Hello everyone. Welcome to a multiple session discussion on semiconductor fundamentals. In this first session, I will be basically discussing upon the atomic structure. In an effort to understand the operation of semiconductors, a fundamental question we might ask is, what is the internal structure of an atom? Please understand that it is not correct to ask what an atom might look like because its components are all smaller than the shortest wavelengths of light that humans can see. Instead, we simply need a model to explain its observed behavior. Perhaps the most prolific model in the popular imagination is the planetary model as shown in the diagram here. In this model, the core or nucleus is drawn at the center and contains positively charged protons and non charged neutrons. Revolving around this core are negatively charged electrons, each following a nice regular planar path, much like a planet around the sun. Unfortunately, this model is starkly incorrect. Before we come up with a more accurate and useful model, let's take a closer look at the subcomponents, namely proton, neutron, and electron. At first, most of the mass of any given atom is from the protons and neutrons. Protons and neutrons have similar masses, about 1.67 into e to the power of minus 24 grams each. The mass of an electron is roughly 2000 times smaller. The radius of a proton is approximately 0.87 into e to the power of minus 15 meters, and the mean distance to the nearest electron is about 5.3 into e to the power of minus 11 meters. This means that this electron is about 60,000 times farther away from the proton than the size of the said proton itself. To put this into perspective, that is roughly the same as the ratio between a golf ball and a sphere with a radius of 3/4 of a mile or 1200 meters. One of the major issues with the planetary model is the idea that electrons rotate around the nucleus in a stable planet like orbits. That is simply not true. First, the electron inhabits a region of three dimensional space. It does not simply move through a plane. Second, due to the Heisenberg uncertainty principle, we can't precisely plot the position and trajectory of a given electron. The best we can do is make a plot of where the electron is likely to be. This is called a probability contour. Imagine that you could record the position of an electron relative to the nucleus. A moment later, you record its new position. A moment after that, you record the next position, and on for thousands of measurements. If you attempted to plot them all, you would wind up with a cloud of dots around the nucleus. This cloud is referred to as an orbital. You would not know how the electron got from one position to the next, but you would get a general idea of where it was likely to be. Do not confuse the orbital with the orbit like a planetary orbit. They are completely two different aspects. There are several potential orbitals. Due to quantum physics, only certain orbitals are allowed. The permissible electron energy levels are first grouped into shells, then subshells, and finally orbitals. It is important to remember that orbitals indicate the electron energy level. That is, a higher orbital implies a higher energy level. Further, orbitals fill in first from lowest energy level to highest energy level. Shells are denoted by their principal quantum number n, which can take on values such as 1, 2, 3, etc. The higher the number, the more subshells it can contain. Subshells are organized by their orbital shape and are designated by letters, the first four being S, P, D, and F. Shell 1 contains only subshell S, while shell 2 contains subshell types S and P. Shell 3 contains subshell types S, P, and D, and it continues in such a manner. Thus, we see designations such as 1S, 2S, and 2P. These subshells may also have variations within them. There is one variation on S, three variations on P, five variations on D, and etc. These variations are the orbitals, and each orbital can hold a maximum of 2 electrons. Putting this all together, we find that the first shell can contain a maximum of 2 electrons, 2 in the single S subshell orbital, and is denoted as 1s. The second shell can contain a maximum of 8 electrons, 2 in the S subshell denoted by 2s, plus 2 in each of the 3 p subshell orbitals denoted as 2p. In like manner, the third shell can contain a maximum of 18 electrons, 2 in the S subshell denoted by 3s, 6 in the p subshell denoted by 3p, and 2 in each of the 5 d subshell orbitals and is denoted by 3d. You can condense this into a simple formula as 2n power 2, where n is the shell number. Figure here shows the electron probability contour of the innermost orbital, namely 1s. As you can see, it is a spherical in shape. The nucleus is located at the center and is not visible here. All of the s orbitals are similarly spherically shaped, although the internals change. Therefore, we note that 1s is the lowest energy orbital. Orbitals, in fact, are not limited to simple spherical shapes. Higher order orbitals can take on a variety of forms. Figure 3 here shows the electron probability contour for the 2p orbitals, and we must recall there are 3 variations for p subshell, one each oriented along the x, y, and z axis. The nucleus is situated in the small void between the two lobes. Obviously, this is nothing like the well-behaved elliptical orbits of planets around the Sun. Probability contours can be very complex. For the highest orbitals, especially when combined with lower orbitals, the contour combinations can become reminiscent of the sculptures of a deranged clown, forming herds of imaginary balloon animals. As interesting as these graphics are, they are cumbersome to work with. Consequently, a more functional graphic is therefore needed. Such a device is the Bohr model, named after the Danish physicist Niels Bohr, and the example of this is shown in figure 4 here. It is important to understand that the Bohr model is an energy description of the atom, not an attempt to mimic its physical appearance or structure. The nucleus is placed at the center. It is surrounded by concentric rings that represent the electron shells. The higher the number, the larger the ring and the greater the energy level. If an electron were to move from a higher level to a lower level, the energy difference is radiated out. This could be in the form of heat or light. This is a point worth remembering. For example, this transition is what makes the light emitting diodes function. The inverse is also possible, namely that by absorbing energy, an electron can move into a higher orbital. This is an equally powerful concept, as we will very soon understand. Using the Bohr model, we can create diagrams to represent individual elements. For example, copper has an atomic number of 29, meaning that it has 29 protons and 29 electrons. The electron shell configuration for the copper would then be 2, 8, 18, 1. That is, the first three shells are completely filled and there is a single electron in the fourth shell. This single outer electron is only loosely bound and thus makes copper a very good conductor. The Bohr model for copper would simply show four rings, the first three being filled and with a single electron in the fourth ring. Figure 5 here shows the Bohr model of an atom of silicon, atomic number of 14 with an electron shell configuration of 2, 8 and 4. You can see the innermost ring has only 2 electrons, the next or the second ring has 8 electrons and the outmost has only 4 electrons. The first two shells are completely filled and the outermost subshell is not filled completely and only has 4 electrons. In this version, the individual electrons are drawn in each shell and the atomic number is indicated at the nucleus, which is 14, as I already have said about. Again, please do not imagine this representing individual electrons orbiting the nucleus in lanes. This is an energy level depiction. Often, it is useful to simplify this model further by omitting the filled inner shells. Also, the atomic number is replaced by the number of electrons in the outermost or valence shell, and this is shown in figure 6 here. The valence shell is particularly important as it gives insight into the general behavior of the material. As an alternative, sometimes we might straighten out the Bohr model so that it simply shows the energy levels graphically as lines or bands and without counting specific electrons. This is depicted in figure 7 here. From this diagram, we note that electrons in shell number 1 will have the lowest energy. Electrons in shell 2, denoted by n equals to 2, will have higher energy than those in shell number 1, and it continues in a similar fashion. Right. I would like to end this session here with the energy level diagram shown, and in my next session I am going to discuss the crystal, particularly by taking the example of a silicon semiconductor material. Thank you.